Yes, thank you. Okay, so today is our third sessions of the tutorials. We continue to talk about the DC circuit. So today we're taking 1 hour to talk about two examples. The first examples, as shown here, is DC circuit analysis. First, let's have a look at the question itself. Then we learn to draw the equivalent circuit and analyze the circuit. So this is one typical applications of the DC circuit in the appliances, right? Okay, so we have a read of it. So the question says, a DC Wheatstone bridge circuit is used to measure the temperatures of an oven. So this is applications, right? Okay. So the temperature sensitive resistance detector R forms one arm of the bridge circuit and is in series with a fixed 200 ohms resistor. The parallel arms comprise a fixed 200 ohm resistor in series with a potentiometer. A potentiometer actually is adjustable resistance. Okay. And to oven temperature of 40 degrees, it is necessary to set the potentiometer at 105 ohms to achieve balance on the milliampere detector. Okay, so the supply source is DC 10 volts with an internal resistance of 100 ohms. So this is the question 10. Okay, so now ask you to calculate the deflections of the meter if the oven temperature falls to 20 degrees and the potentiometer is not adjusted. Okay. Given that the temperature coefficient of the resistance of the R is 0.0025 degree per degree at 20 degrees. So this question that we have a so-called Wheatstone bridge circuit. So this circuit has two arms in parallel. These two arms is supplied from a 10 volts DC source that with an internal resistance of 100 ohms. Okay, so one of the ohm is fixed 200 ohms in series with a temperature sensitive resistors R. The other one is a 200 ohms fixed resistance in series with adjustable resistors. Okay, in practice, we can adjust the adjustable resistors so that two arms be balanced. So therefore, we can read the readings of the adjustable resistance to get the temperatures of the ovens. Okay, so now we go ahead to see how to draw the equivalent circuit. We can, based on the equivalent circuit, have a further explanations of the questions. Okay, so to the next slide. First, that's looking at the equivalent circuit I have drawn here. The question said that this is a Wheatstone bridge circuit. Okay, so it includes two arms in parallel, so arm 1 and arm 2. Then it's supplied by a DC source which has a 10 volts internal electromotive force with 100 ohm internal resistance. The arm 1 is 200 ohms fixed. This is fixed, right? In series with a temperature sensitive, right, resistor, temperature sensitive resistor. So this resistor changes with the temperatures. It is plugged into the ovens to detect the temperatures. Okay, So this is so-called sensor. In practice, we have different types of sensors. Some sensors is sensitive to the humidity. Some sensors is sensitive to the temperatures. Some sensors sensitive to the pressures, and so on. So here we have a resistor that is sensitive to the temperatures, that used to detect the temperatures in different places. One of it is the oven. So if you in the futures you are asked to design some of the detectors, you can using the temperature sensitive resistors or humidity sensitive resistors or the other sensitive resistors to detect the environment's temperatures, environment pressures, environment humidities, and so on. So that's the sensor. So basically speaking, in applications, we can try to find out different devices that can that its resistance changing with the environment. So we have many kind of materials. That's the sensors. Okay, so this is one branch. So we can monitor the branch, right, with currents use small ammeters, in series with this branch. Another branch is also right with a 200 ohms fixed resistor in series with a potentiometer. So now this potentiometer actually is an adjustable resistor. So we can change the resistors here. In practice, we do not know the accurate values of the resistor here. When the temperature change, these are changing. So on the other side, we can adjust the potentiometer. Here we using the RP. P stands for potentiometers. We can adjust this RP so that the current on this branch 1, on branch 2, be balanced, be the same. Then we can say using this resistance to say the values of this resistance, because they are balanced, Rp equal to R. And then for a given resistance of the R, it corresponding to a given temperatures. So here we can mark the temperatures for different values of the Rp. So this is the principles of this circuit. Now we back to the circuit analysis. So here we first looking at the arm 1. Arm 1 here, this arm 1. It is said that at 20 and 40 degrees, we have to adjust the RP to 105 ohms so that the two branches are in balance. So that means at 20 degrees, so the RP is 105 ohms, and the R at 40 degrees is also 105 ohms. So because they are balanced, right, at 40 degrees, they are balanced. On the other hand, it is given that the temperature sensitive resistor R has a temperature coefficient 0.025 per degree at 20 degrees and 20 degrees. Now, comparison with the 40 degrees, suppose the 20 degrees resistance is R20. Then the resistance at 40 degrees related to the resistance at 20 degrees, is given here, which we learned in the first class already. So the temperature coefficient, this is the is the 40 minus 20. So this 20 is not 20 degree. This 20 is the 40 minus 20. Okay, that's the temperature difference. Okay, and this is temperature coefficient. Okay, this is the 40 degrees resistance, which is given 105 ohms. Okay, so from the given conditions here, we can have an estimation about the 20 degrees resistance of the temperature sensitive one, okay, which is 100 ohms. Okay, 100 ohms. Okay, this is the right. Okay, from the given conditions, we can guess that the resistance and 20 degrees R is 100 ohms. Now, okay, for the case, then when the temperature is back to 20 degrees, back to 20 degrees, then for the branch 1, it has 20 degrees resistance, which is 100 ohms, and fixed 200 ohms. So the total resistance in branch 1 is 300 ohms. For the branch 2, it keeps no change. That is, the potentiometer has 105 ohms, and the fixed 200 ohms. Together is 305 ohms. Okay, because now the temperature is down to 20 degrees, and the branch 1, the R, gets smaller, which is 100 ohms. Okay, so with this resistance in branch 1 and this resistance in branch 2, okay, we can estimate the total system resistance referred to the source. Okay, source is 10 volts here. Source is 10 volts here. So looking into the system from two terminals of the source, from here and here. Okay, from two terminals. Okay. So for a two-terminal source, looking into the systems, the total resistance is 100 ohms Ri in series with these two branches in parallel. So these two branches in parallel. So that means the branch 1 R1, okay, the branch 2 R2 in parallel, and then in series with Ri. Okay, so we can bring in the Ri 100 ohms, the R1 300 ohms, the R2 305 ohms. So you just have a simple calculation with the calculator. You can find out the total resistance referred to the source. Okay, we said the total resistance referred to the source. So okay, so here what we calculated is the total resistance referred to the source. Some students might say that, can I, using the other ways to estimate the current distributions in the systems? Yes, you can do that. You can using the choosing one loop, another loop to establish the equations, two loop equations, right? So you can use in this loop, you can use in this loop, right, to establish the equations. Okay, so but here we're using a more straightforward way to estimate the currents. Okay, so we got the total resistance referred to the source. Then we can estimate the total current out from the source. So the total current out from source Okay, so with the total resistance referred to the source, okay, and the source resistance, we can estimate the total current out the source. So the total current out source using the 10 volts over the total resistance, which is 250, okay, 51.2, we can estimate the total current out the source is about 39.8 milliamperes. Okay, milliamperes. So that is the I here. Okay, now how much is the current on branch 1? How much is the current on branch 2? So we can directly using the previous, right, okay, empirical right, formulas that for two branch, okay, okay, with the total current given, the two branch share the current in a way that in branch 1, okay, it shared the ratios, okay, is the branch 2's resistance over the total resistance of the two branch. Okay, so that is the branch 1 currents equal to the total currents times the branch 2 resistance over the total resistance on branch 1 and branch 2. Okay, so we can estimate that the current on branch 1 at this moment is 20.1 milliamperes. And meantime, that the current on the branch 2 can be estimated in a similar way. That is, okay, the total current times branch 1's resistance over the total resistance. So which is estimated 19.7 milliamperes. Okay, so the total is 39.8 milliamperes. So the difference between the branch 1 and branch 2 has been found. Okay, has been found. Okay, here we just using one straightforward method, okay, to do the calculations of it. In practice, you can use a different approach to analyze such a circuit. Not limited to this one way, and you can estimate, right, okay, loop circuit here and a loop circuit here. So you can have a loop circuit, this loop circuit, and you also can have a this loop circuit. You got two equations so that you can estimate, right, okay, the current distributions. Okay, for examples, we using, okay, this and this. We can estimate, okay, two, okay, equations so that we can find out, okay, the current R1 and R2. Okay, so first for loop 1, for loop 1, we can start from the R. Okay, so the R, okay, so because the current is downward, okay, so we start from the lower side of the R, okay, in the clockwise direction. Okay, for the loop 1, we in clockwise direction and start from R. So the R, okay, which times I1, okay, times R1. Sorry, we direct right R1. Okay, that's better. R1. So we ignore the voltage drop cross the ammeters. Okay, and plus the 200 ohms, I1. K R1. This should equal to, okay, or the student's method would directly use in the, okay, in the Kirchhoff voltage law, minus 200, okay, I2, okay, 200. Make the things be clear. I2, okay. Okay. And minus, okay, the RB times I2 equal to 0. This is the equation 1. Okay. So for the loop 2, we count in clockwise direction and start from the potentiometer. Okay, so the RP, okay, times the I2. Okay, so this is the voltage up. Okay, plus, okay, the 200 ohms times the I2. Okay, then minus, okay, the 100 ohms, okay, times, okay, the total current, which is I1 plus, okay, the I2. But here, because the current is upward to the R1, so the upward to the R1, but we count the loop in, okay, counterclockwise directions. So here will be plus. Okay, get to the point, will be plus. And also, okay, because here, so the current, total current I, which is the sum of I1 and I2, okay, I2, is upward, okay, it's upward. Okay, so the source here actually is upper, higher, okay, and the lower actually is lower. So this is a voltage, okay, this is a voltage drop, right? Okay. 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 So we have equations. Yeah, equation 2. Okay. So here we just give you one examples that, okay, what I show here is a straightforward method, but you can still using the Kirchhoff voltage law or the Kirchhoff current law, choosing two loops, one loop here as I show here, so another loop, loop 2, show here. You can establish the voltage potential drop equations. For loop 1, so start from the resistance R, suppose the current downward, okay, so then, okay, it is, okay, so the R1 R times R1 I1, okay, plus, okay, 200, okay, times R1. So because current downward, so the voltage drop, voltage up, and to the branch 2, so I2, the downward, so 200 ohms has voltage drops because the current from high potential to low potentials. And for the IP, so the current downward, the voltage drops. So up, 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 drop, drop equal to 0. Now, coming to the loop 2, so we start from the RP in counterclockwise, in the clockwise direction. So the RP with the current I2 voltage up. The 200 ohms with current I2, the voltage up. And coming to the source side, so the source internal resistance 100 ohms, and the current I, which is the sum of the I1 and I2, according to the Kirchhoff voltage current law. So the current is upward. So the voltage cross the internal resistance 100 ohms downward, actually is upward, is upward. So voltage upward, upward, upward. And looking at the source, 100 ohms, so 100, so 10 volt source. Sorry, there is a typo. 10 volts. 10 volt source. So the 10 volt source, because we now count in clockwise direction. So when in clockwise direction, but here is a voltage drop, right? Voltage drop. Because the current in this direction, here voltage drop. Okay, so we have the equation 2. Okay, so combine these two equations together, you can obtain the similar results as I show here. You got R1, R2. So please do it as an exercise, to see whether you can correctly solve the two equations and got the correct solutions of it. Okay, so if you still have any questions on these examples, you can write down using the chat box, at this moment, or you can write to me after lectures and so on. If no questions, we continue to looking at the second example, which is a relay circuit. Okay, anyway, so we have take the records of these tutorial sessions. What I write here, so you can check again, after the lectures. Okay, this is one examples. Of course, we have many such examples, but due to the because the time limits, we cannot raise a lot of examples in the lectures and in the tutorial sessions. But you can find out more similar exercise in the reference books, wherever you can find out to get practice. Okay, so this is the second examples I would like to talk today. This is a relay circuit. Before I talk about it, I would like to further to clarify some of the concepts that may confused with some students. So Hmm? Okay, so when you read some books or in lectures, you always hear that sometimes we say a circuit, sometimes we say a cable, sometimes we say a core, or a conductors. They are different. They are different. In a DC circuit, a DC circuit, okay. So a DC circuit consists of two cores or two conductors, or we say a two-core cable or two single-core cables. Typos. Okay. Or two-core cable or two single-core cables. So, okay. So this statement is very important, for you to understanding, the questions. Repeat, a DC circuit consists of two cores or two conductors, or we say a two-core cable or two single-core cables. Okay, so that's the difference between a circuit, a cable, a core, a conductor, and their relationships. Okay, now we move to this question itself. Do not confuse with the concepts again. Okay, we have two loads of 50 amperes and 30 amperes respectively. I connected to a radial distributor at a distance 200 meters and 300 meters respectively from a 120 volts DC supply source. The distributor cable is 25 square millimeter two-core armored PVC insulated copper to British standards 63 and 46, which can be found out in the tables A64. Find the potential difference across each load and the energy loss in the cable over a 24 hours period. Okay, so what do we draw here? And that means we have one source, which is 120 volts, and we're using two-core cables. This cable is armored PVC insulated copper cables. The core cross-section area is 25 square millimeter each core. It has two core each core. And at 200 meter, at the position 200 meter, we have one load, of course, in parallel to this circuit, which using 50 amperes currents. Another 100 meters away, from the first load, we have a load that using 30 amperes. Okay, so we're using a two-core cables here. Okay, the cable specifications can be found from the table A64, which I showed you in the previous sessions. and which is attached with your teacher notes. Here we do not check in detail about it. We just focus on how to analyze these questions. Okay, so this is just the circuit drawings, but we should know that internally, okay, each circuit has two cores. And we go ahead to see how to draw the equivalent circuit of it, and then to find out, okay, the voltage at each load there. Okay, so this is the equivalent circuit that we draw here. So this is the source, which is 120 volts. So it has two conductors, conductor 1 or core 1 or the core 2. They are in one cables, okay, in 1 2 core cables. So the source 120 volts. So we have this cable, remember. So this cable has voltage drops. The cable has a resistance. That is the voltage drops here. The table has a resistance. The voltage drop per ampere per meter. Okay. Okay. To make things more clear, I write down, okay, one sentence here, okay, to clarify issues. So as I said, the cable has resistance, which will cause voltage drops. So the cable resistance values can be found, right? Can be got from the table A64. So what's it? That is the voltage drop per ampere per meter for two conductors given. Okay, for voltage drops per ampere, if the current is 1 amperes per meter long for two conductors together. So voltage drops, okay, voltage drops. Okay, that's it. Okay. Now back to these questions. So so this is the old tables. Okay, old tables. Okay. In this case came from right for the A64, right? Okay. Okay. So from the A64 cables, you can find out the voltage drop for two cores is 1.75 millivolts per ampere per meter. Okay. So this cable, of course, is for the cables 25 square millimeter. Okay. For the cables of 25. Okay. So please check in the tables about the 25 square millimeter two-core armored PVC, right, cables. copper materials. Okay, so you can find out readings of it. Okay, so now, so this is the resistance issues. Okay, but we do not draw here in practice because we do not use in direct resistance, but using voltage drop per ampere per meter values. Okay, so now, so from the source, okay, looking into the different loads, we're looking at the so load C, position C. The node 2 using current 30 amperes I2. We suppose this direction. The node 1, we have the current, right, I1 in this direction and these directions. So for the position C, okay, position C, the I2 is 30 amperes. Okay, so here we have nothing. Okay, we have nothing because open. Okay, we have nothing. Okay, so we have C here. Okay, the cables may be longer, but doesn't use it, right? So no anything be here, no anything be here. So that's the practice. Okay, so for the future uses, right? Okay, so load B, okay, load B here. So the current of the cross the load B is 50 amperes. So the resistance can be estimated. Okay, maybe you can use in a resistance. This is R1. Okay, is 1. Okay, RC. Okay, they have RB. Okay, so you have RC, RB. Okay, you can estimate it later on. Okay, not here. So anyway, so for the load B here, so the current I2, okay, and R1 in, okay, I2 out, and 50 out. So we can estimate the R1 equal to the I2 plus 50 amperes, that is 80 amperes. 80 amperes. Therefore, we can looking at the voltage drops. We can use in one loops, the loops A, B, B1, and okay, A1, A. So that's this loop, okay, A, B, B1, A1, A loop in counterclockwise directions. So the source 120 volts, okay, then supply to the load B and the two conductors here. So first, the voltage drops on the two conductors 200 meters long is current I1 200 meters long and voltage drops per ampere per meter in volts. Okay, so this is millivolts per ampere per meter for two conductors. We check into the volts per ampere per meter for two conductors. So now the two conductors, the cable 200 meters long, the current. So this is currents, this length, this is the voltage drops per ampere per meter for two conductors. So someone said that why you didn't times the 2 here, but because this is already is the 2, okay, together. So the voltage drops cross the load B, we suppose is VBB1. So this is the for these loops we can find out. Okay. Now we can looking at another loop that is the A, C, C1, A1, and A. So similarly, we have the 120 volts, that's the source volts, equal to the voltage drops, the other parts of it. Okay. So the voltage drops, that is 200 meters long with I1 and 100 meters long with I2. Okay. And the voltage drop per ampere per meter, the same cables here is 0.00175 volts per ampere per meter. And the voltage cross the C and C1 is VCC1. So we have two of these equations. Since the R1 is 80 amperes. I2 is 30 amperes. So we can easily estimate that the voltage across the load B is the source voltage 120 minus the 28. This is what it drops. Okay, so this is the source. This is what it drops. Okay, this is what it drops. So at the end, the load B has a voltage 92 volts, much lower than 120 volts. Okay, volts. So this is the case in practice. You look that the voltage drops across the cable is a bigger problem in practice. That's why we have chosen suitable size of the cables so that the voltage drops do not rise so big. Now, for the load, okay, C1, okay, the source voltage is, okay, 120 volts. The voltage drops across the first 200 meters is 28. Okay, first 200 meters is 28 volts. And the voltage drops across the second 100 meters long, which is this parts is 5.25 volts, very small. At the end, the voltage across the load C is 86.75 volts, much lower than 120 volts expected. Okay, so this is one case of it. So you found that the voltage drops on longer cables is bigger. Voltage drops on longer cables bigger. The larger of the current, the bigger of the voltage drops. The longer of the cables, the bigger voltage drops. The table values is the voltage drops per ampere per meter for two conductors. Remember this one. Okay, per ampere per meter. Okay. Now that has estimations about power losses on the cables. First, for the first 200 meters, it has a current 80 amperes. It has a voltage drops 28 volts. So the power consumptions on the first 200 meters long cables is 80 amperes times 28 volts. Similarly, the power losses on the second 100 meters cable is 30 amperes times 5.25 volts voltage drops. Okay, this is powers. The total powers is the sum of them. Over 24 hours is the total energy losses. So the total energy losses here over 24 hours is estimated as 57.54 kilowatt hours. This is one unit, a unit powers, a unit energies, a unit energies. So kilowatt hours is a unit energy. In Hong Kong is about $1. Okay, so this is about 60 Hong Kong dollars. So this is about 60 Hong Kong dollars cost, losses. Look, so this is the energy loss on the cables, Okay, so in practice, our homes using the electricity and the power company just charge the power consumptions in homes, but actually they got energy losses along the distribution line, very long distance power distribution lines. So therefore, the residential buildings electricity cost price is a little bit higher than that for the industry one, because we usually has small power consumption in the home, but has a long distance power losses, okay, on the transmission lines. Of course, this is a very simple example that we have just two loads on the same cables at different distance from the source. So this is very the common way of the power distributions in the buildings. Of course, with the increase of the high-rise buildings in Hong Kong, so we have many loads that far away from the source. So we usually has very long distribution conductors inside the cables, inside the buildings. For example, for a 100-meter higher, 100-meter high buildings, if we have the transformer rooms on the ground floor, we should use big cables to distribute electricity from the ground to the top of the buildings, so that the voltage drops on the distribution cables be small. For example, on the ground level, if the source voltage is 220 volts, if the cable is just 25 square millimeter, then the voltage drops along 100 meter cable for 100 amperes, using the current maybe is about 220 volts. That's terrible. The source voltage is 220, but your voltage drops will be 200, right? So at the end, right, on the top buildings, we cannot use the electricities. So we should use big cables. That man has a cross-section area is about 120 square millimeters, so that the voltage drops be very small. That's the problems of the cable sizings. In next semester, you will learn about in the year, next year you will learn about the cable sizings based on principles we learned today. So that's the cable sizing problems. Is the concern about the voltage drop issues. In Hong Kong, generally, for the final circuit, the voltage drops, maximum voltage drops maximum voltage drops from the source. We said transformers. The voltage drop from source, that is the transformer, to load, the voltage drop from the source to load should smaller than 4%, and from distribution board to or MCB board or distribution board to load, that is the final circuit, should smaller than 2.5%. The source So in Hong Kong, in our Hong Kong, so the voltage drop from the source transformer to the load, so it is a long distance probably. So the total voltage drops, on the distribution line should smaller than 4%. Okay, among this 4%, from the final MCB board, distribute board to load, in the final circuit, the voltage drop should smaller than 2.5%. So between the source, okay, to the final distribution board, okay, the voltage drop allowed is 1.5%. Okay, very small. And meanwhile, the source itself may have fluctuations. So that fluctuation must be smaller than 6%. Okay, so in total, the voltage fluctuation, okay, usually is voltage drop. Okay, the total voltage drop, okay, from the source to the load, in comparison with the rating voltage, should within 10%. That's why you look that in the buildings, for most of the single-phase users, the standard voltage is 220 volts. But the loads should be able to work when the voltage between 200 volts to 240. Okay. Rating, for example, if the rating is 220 volts, okay, the load range, okay, range is 200 to 240 volts. Okay, so generally, if you check into many right transform many machines, so their rating voltage is 220 volts, but they can work, okay, effectively within the range of 200 to 240 volts. So they can work well. But if the voltage beyond this range, so the machine stop to work. All the machines has standards. Okay, the machines is standards. Okay, so that's the case of it. Okay, so the time is out. So this is today's tutorial sessions, which will be repeated this afternoon. Okay, now see you next times. Okay, that's the end of this tutorial session. Bye.